Here we have some more nonlinear examples, this time involving an absolute value equation. So we're going to solve an absolute value equation and inequalities using the graph. It is the same absolute value statement on the left in all three. So we're going to see, we'll be able to use the same graph for that absolute value. In particular, negative absolute value of 2x plus 6, close absolute value, plus 4 is equal to 0. And then we'll look at when it's less than 0 and when it's greater than 0. I've graphed the absolute value function, y equals negative absolute value of 2x plus 6, close that absolute value, plus 4, on the in Desmos, and I have it available here. Notice you don't see another graph. That's because when I graph y equals 0, that's really just the x-axis. So there's no reason to graph y equals 0. We can actually see it just on the x-axis. It would just basically be a line over top of the x-axis. So in all three of these statements, we are actually comparing the absolute value graph to the x-axis. Now with the equation, we're saying when is it on the x-axis? So let's pick that out. We've got 2 points where this V-shaped graph crosses the x-axis. Let's take a look at this. First one on the left would be a value of, or point value of negative 5, 0. The one on the right would be negative 1, 0. So the solutions would be the x values. So the solution set would simply be the x values of negative 5 and negative 1. Now we just want to show those individual values, so we use braces. So we use a brace on each side. That's the way to represent a set of individual values. We could check those as we would any equation by plugging those values back in. We could also solve that equation algebraically. We learned how to do that earlier in the chapter. So I'll check this later, but let's go on to the inequalities next. The middle inequality here, or the first one as we go down the page, has a less than. So we're looking at when is the absolute value graph less than 0 or below the x-axis. So when we go over this V shape, because this V is opening down, it ends up being below the x-axis on its two ends, here and here. So one area on the right, one area on the left. These are separated physically, so we're going to have to use two separate intervals for those. The one on the left, if we look at what x values are on, would relate to that, would be values going out to the left, which would mean negative infinity, and then it stops on the right at negative 5. And because this is a strict inequality, no equals, we would not include the endpoint there at negative 5. So use a parenthesis. We're going to union the other side, because they are separate, we have to write them separately. The other side starts at an x value of negative 1. And be really careful here. You're going to continue out to the right. So the graph is going down, but it's going to the right. The x values are actually values to the right. Be careful. When you go to the right on a grid like this, we're going out to positive infinity. Sometimes when people see the graph going down, they want to say it's going to negative infinity, but that would be the y value. What we care here for solutions is the x values. So our solution set for this less than inequality would be the union of two individual intervals of numbers. Negative infinity to negative 5, union negative 1 to infinity. And again, you don't include either negative 5 or negative 1 because of the strict inequality. The last statement here has a greater than. So we're looking at a greater than symbol here. Whoops, I was trying to use a highlighter and it didn't work out very well. So this was originally a greater than symbol. Greater than 0, the absolute value greater than 0. And then we want to consider when it is above the x-axis to solve this. So above the x-axis would be the V part of this graph, the part that is above the x-axis. The x values in that interval are from negative 5 to negative 1. So my solution set would be just from negative 5 to negative 1, again, not including those particular endpoints because of the strict inequality. So I've got all my solutions here for both the equation and the two inequalities. If we wanted to check With an equation, we're just checking that these individual values really do make this statement true. So we would plug in those individual values. So negative absolute value of 2 times negative 5 plus 6, close the absolute value, plus 4 equals 0. So we'd calculate inside the absolute value first. 2 times negative 5 is negative 10, plus 6 is negative 4. Then calculate the absolute value itself, keep the negative outside. So the absolute value of negative 4 is 4, but there's a negative out there. Plus 4 equals 0. And of course, negative 4 plus 4 is 0 itself, so that works. You can get a similar result by plugging the negative 1 in. I'll leave that one for you to check. And then checking the inequalities, we would check values inside of the sets. So with this one, you would check something in this region. So like negative 6. Here you would check maybe 0 would be in this region. And then I'll just check one that is in this last inequality set, which would be like, for instance, negative 2. So if I check negative 2, the absolute value of 2 times negative 2 plus 6, close the absolute value, plus 4 is greater than 0. Calculating 2 times negative 2 is negative 4 plus 6 is 2. Then the absolute value of 2 is 2. Negative 2 plus 4, that is going to be 2. 2 is indeed greater than 0, so that region seems to check out. So we get all of our solution sets here that can be checked pretty easily just by hand or by re-examining the graph a little bit more thoroughly.